Okay, this will be our last video. In this video, we're going to talk about polynomial and rational inequalities. So I like to start with a simple introduction, just using the parabola or the quadratic function to kind of give a little bit of an explanation. So we had a quadratic function. We usually represent it with this formula. That's one way we can do that. Okay, where we have y equals ax squared plus bx plus c. When we solved a quadratic equation, we didn't have the y there, we had a 0 equals ax squared plus bx plus c, and we solved for x. The way these two relate, right, when we put a 0 in for y and then we solve for x, that's kind of a process we've been practicing, right? That's how we find the zeros or the x-intercepts. For a parabola, we could have three possible results from that, right? We could solve that equation and get two answers, two real numbers as our answers that are the x-intercepts. We could maybe see a repeated part in our factoring, or maybe we just have a repeated 0. So in that case, the parabola would just touch one spot on the x-axis. We get one solution. Or maybe it doesn't touch the x-axis at all. We had this on a worksheet a couple of weeks ago, right? And in that case, we would have two complex number solutions. It doesn't touch the x-axis, so it doesn't have any real solutions. Okay, so that's the equation, right? When we have an equals. In this video, or in this section, we want to look at what happens when we have an inequality, a less than or greater than. So we're not going to be looking just at the x-axis, but we're going to be looking at the parts of the graph around the x-axis, right? For greater than, we're going to be looking at which parts of the graph are above the x-axis. For a less than, we're going to be looking at which parts of the graph are below the x-axis. Since our question or problem is going to look sort of like this, notice there are no y's here, just x's. So the solutions that we get are going to be a set of x values. So we're going to say numbers from this x to this x are possible solutions. And we're going to use interval notation to describe those. There's two possible methods that you could use. So we'll take the time to develop both of these. We're going to look at both polynomial inequalities and rational inequalities, which would be a fraction. And these two methods actually work for both. So you can either graph the function and do what we were just talking about, where we compare it with the x-axis, whether it's above or below. Or there's a second method you could use that involves a number line, where you're testing values to see if the values in a particular region are solutions or not. And this is maybe a more computational method. So if interpreting from a graph was difficult, this one we're just plugging in values to do a test, and sometimes that's easier depending on your personal preference. Okay, so we're going to start with a parabola type example, and we're going to do the same problem with both methods so you can see how they work. So for the graphing method, to solve by graphing, we're going to solve the corresponding equation. So we're going to take out the less than or greater than and put in an equals and solve. And that's going to give us the x-intercepts, the points that we were just plotting on the x-axis. Then we're going to graph the equation. It might be a parabola, it might be a polynomial where it's a squiggle. Okay, we're going to fill in the graph shape, kind of as a sketch, not a detailed graph. And then we're going to look, like we said, we're going to compare with the x-axis. We're going to look if it's greater than in our question, we're going to look for parts of the graph that are above the x-axis. If it's less than 0, we're going to look for parts that are below the x-axis. And then just like we just said, we're going to use x values and interval notation to describe the solution. Okay, so here's an example. Let's say we have x squared minus 5x plus 4 is greater than 0. So we want to know what x values will make this whole expression here positive or greater than 0. So we're going to just kind of follow these steps. We're going to start by putting in an equal sign. And a lot of these can be solved by factoring, but if for some reason you couldn't factor, you could use the quadratic formula or any of those other tools that we've been practicing with. This one is factorable. So I need two numbers that multiply to be 4 and add to be -5. I think -1 and -4 should work well. Okay, so then I'll set each part equal to 0. I'm not going to write that out just because we've done it so many times at this point. So if I set x minus 1 equal to 0, I'm going to get +1. If I set x minus 4 equal to 0, I'm going to get +4. Okay, so I need to know, to make this kind of rough sketch of the graph, I need to have a good idea of the graph shape. Because I have an x squared, I know this is going to be a parabola. Okay, I know it's going to have these x-intercepts. The only other thing that I might need to know is whether the parabola opens up or opens down. So I'm going to make the graph over here. Why don't I write, this is what we're graphing. You could definitely use your calculator for this part. Okay, but just know that on the test you're going to have to show some supporting work. So you do need to show a graph. You can do it on your calculator, but you need to make a sketch of it on paper so I know that you did look at your calculator, or I know that you've seen the graph at some point. And you do need to label these points, the x-intercepts, because those are really important for problems like this. Okay, so this is a +1 x squared, so this parabola opens up. So if we were to graph this, we have an x-intercept at 1 and at 4. Okay, normally we would find the vertex, but right now we don't really care about all those details. We just want to know where it's above and where it's below the x-axis, because that's what we're using to solve this problem. Okay, so now that we've graphed it, are we looking for parts of the graph that are above or below the x-axis? We're greater than 0. So we want to look above, right? Greater than 0 means we were looking for y values that are positive, and those are going to happen above the x-axis. So for a parabola, not all of these are going to be parabolas, but for a parabola, this is either going to be the middle or the ends usually, okay? Since we're looking above the x-axis, it's going to be the ends. These two pieces right here are above. So that means the x values that go into making these branches of the graph are going to be from the left on and from the right and on the right hand side. I'm losing, my pen is running out of ink. Okay, hopefully you can kind of see the ghost of that. All right, the next question we need to decide is, are we going to include the 1 and the 4? The 1 and the 4 are where this expression is equal to 0. Do we want to include the places where it's equal to 0? And for this problem, the answer is no. We don't have the equals bar here. We're just looking for the parts that are greater than 0. I bubbled these in just to make the graph, but if I'm not going to include them, you might want to draw in some open circles. Maybe I'll do this since my pen is not so good. So all of these x values on the ends will make the two parts of the graph that extend above the x-axis. So my solution is going to be the x values from -infinity up to 1. We do not have the equals bar, so it is not including 1, so round parentheses. And then skip the middle, because that's below. And then from 4, same thing here, no equals bar, so round parentheses up to positive infinity. This is my final answer. Okay, so this is a good demonstration of the graphing method. We make a sketch of the graph, we pay specific attention to the x-intercepts, and then we either look above the x-axis or below the x-axis, depending on our inequality. Let's take a look at the other method. So the second method uses a number line. The process is very similar, but instead of having a two-dimensional graph with a y, we're not going to have that. We're just going to have a one-dimensional number line. And we said this one's a little bit more computational. Right? So we're still going to do the same first step. We're going to solve the corresponding equation. So we're going to put in an equal sign and solve. And then we're going to draw a number line that's separated by the solutions that we get. Sometimes these solutions are called critical points. So we're going to mark those on our number line. And then that's going to divide the number line up into intervals or sections. And we're going to test a value, test a number in each section. All the sections act the same. They're either all solutions or all not solutions. So we just have to test one number to see if they work or not. And then, just like before, we're going to write our solution with interval notation. So for this problem, the first step is the same. So I'll just kind of recopy it here, but I know we just did the same problem. I'm going to put in the equal sign and solve. We said this one is factorable. And we got 1 and 4. Okay, for this method, we're going to put these numbers on a number line. And so the 1 and the 4, because there are two numbers, two x-intercepts, two critical points, it's going to divide the number line up into 3 regions or 3 intervals. Okay, we want to test a number in each of these 3 regions. We don't want to test 1 and 4. We already know what 1 and 4 do. They make the whole thing equal to 0. We want to test numbers in between 1 and 4. So something smaller than 1, you can pick any number you like. 0 is a really easy choice. Okay, pick a number between 1 and 4, maybe 2. And then pick a number greater than 4. 5 might be a good choice. Any number is fine. Okay, and then I want to plug them in to see if they make the expression here positive, bigger than 0, or negative. And I'm going to mark that on my number line. Okay, so if you like to use the number line method, you need to show a number line, and you need to show that you've tested values in each region. So you do have to have supporting work for these, and that's kind of important. Okay, now I'm going to write this out. Even though I would normally do this part in my head, I'm going to plug in these numbers. You can do it any way you'd like. You can plug into the original if you want. I personally like to plug into the factored version because I can do that in my head. So I'm going to write it down like I said, but normally I would just do this in my head. So if I plug in 0, I'm going to have 0 minus 1 times 0 minus 4. So that's negative 1 times negative 4. So that would be positive 4. And I don't really care about the 4. I just care that it's positive. So that means that any number I picked in this region that's smaller than 1, all the way down to negative infinity, when I plug it in, I'm going to get something positive. Okay, same thing for 2. I'm going to plug in 2 for x. So I'll have 2 minus 1 times 2 minus 4. So that's 1 times negative 2. So that's going to be negative 2. Same thing here. I don't really care about the 2 part. All I really care about is the negative. All right, last, I'm going to plug in the 5. So I'll have 4 times 1, which is a positive 4. All right, for this example, I'm doing greater than 0, which is positive. So I'm looking for the pluses that I've drawn here on my number line. Some people like to use checks and X's. You're welcome to use anything. On the test, I would recommend using a number line. If you use this method, I would recommend drawing the number line and writing down pluses and minuses or checks and X's or something to show that you've done a test. Okay, so we want the pluses, so you could shade those in if you like. Just like in the last method, we need to decide, are we going to include the 1 and the 4? Because there's no equals bar here, we are not including those. So I'll do open circles. And then we're going to write our final answer using interval notation. Round parentheses again because we are not including the 1 or the 4. Okay, so that's giving you a good picture, I hope, of the two methods that you have to choose from, the graphing method and the number line method. I'm happy for you to use either one. Whatever appeals to you the most is totally fine. Okay, so let's try these out on some different problems now. Here is a polynomial inequality. So it's not an x squared this time, it's not a parabola, it's an x cubed, okay? And I want to give you a chance to see both methods here as much as I can. So the first step, no matter which method you use, you have to put in the equal sign and find either the x-intercepts or the critical points. So let's start with that. This one is factorable. Notice there are 4 parts, so we can do factoring by grouping. The GCF for the first pair would be x squared. The GCF for the second pair would be a -1. Okay, notice the parentheses match here, so we can factor out an x minus 4. And an x squared minus 1 is a difference of 2 squares. So if you wanted to, you could even go one step further. And if I set all of these equal to 0, 1 by 1, I'm going to get 3 x-intercepts, or zeros, 4, -1, and +1. Okay. So depending on your method, you at this point either want to make a graph or a number line. I'm going to start with the graph, and then I'll go back and fill in the number line. You do whichever one you like the best. You can even skip around on the video if you like. Okay, so if we start with the graph, we can put on our zeros. We can put on the end behavior. Notice x cubed is the dominating term. The +1 out front. So that means that the right-hand side is going to go up. Because the exponent is odd, the ends are going to go in opposite directions for this one. Okay, I'm not going to write out the chart because I don't want to take up the space to do that, but notice in the factoring here, each of these factors only happens one time. So that means for all of them, we're going to cross over the x-axis. And we're going to estimate the turning points. Remember, we don't really care specifically about the turning points. We just care where we're above and below. So we're going to cross over, have a turning point above, then cross over again, have a turning point below, and then meet up with the right-hand side. Okay, are we looking for parts of this graph that are above the x-axis or below? It's less than 0, so we're looking for below the x-axis. So this left-hand end is below. This is above, so we're going to skip that. And then this is below right here. So we have two regions. I didn't label these, but we can do that. Okay, so if we write this in interval notation, we're going to go from negative infinity up to -1. Oh, I forgot to ask. Okay, are we going to include the zeros? The answer is no. We don't have the equals bar under here. So round parentheses. If we had the equals bar, we'd do the square brackets, but we don't. Okay, and then from 1 up to 4. All right, now let me draw the number line for you so you can see how that would match up. I'm going to put -1, 1, and 4 on the number line. And then we're going to test values in each region. If that made it better or not. Okay, so anything smaller than -1, -2 maybe, in between -1 and 1, 0 would be a good choice. Something between 1 and 4, 2 would be a good choice. And something bigger than 4, maybe 5. Okay, we're going to plug it into our factored format. Okay, and we're going to plug this in. Again, we could probably do this part in our head if we wanted to. Let's move this up. But I'll write it down one more time. So if I plug in -2, I'm going to have -2 minus 4. That's going to give me -6. -2 plus 1 would be -1. And -2 minus 1 would be -3. So if I multiply all three of those together, I'm going to get -18. And like we said before, the negative is what we care about. If I plug in 0, I'm going to have -4 times 1 times -1, which will be +4. So positive. If I plug in 2, I'm going to have -2. 2 plus 1 is 3. 2 minus 1 is 1. So that's going to give me -6. So negative. And then if I plug in 5, I'm going to have 1 times 6 times 4. So that's +24, which is positive. Okay, if we go back to the original problem, we are less than 0. So we want to look for the negatives that we've marked. This would be in this region, and this region. It's not equal to, it's just less than, so we are not including the endpoints. All right, and we're going to get the same solution that we got, and I'll just not write it since it's already written right here. Okay, notice how these parallel, right? They're two different ways of coming about the same result. If when my graph is below the x-axis, I got a negative. When my graph was above the x-axis, I got a positive. This is the y value that's positive, right? When I got a negative, I was below. And when I got a positive, I was above. Okay, so it's doing the same process. It's just the graph is a two-dimensional way to do that, and the number line is a one-dimensional way to do that. So this looks a little bit different, but the result is the same. Okay, so now we're going to take those same two methods and apply it to a rational inequality. So this would be those functions that were our fractions. Okay, and we have the same two methods. We can use the graph or we can use the number line. The graphing method is exactly the same. The only difference would be that we're interested in finding, I'll just put this as a side note. We want to find the x-intercepts. And we want to find the vertical asymptotes, right? Because those two things, two characteristics, are places where the graph could change from being above the x-axis to being below. So we need to be really mindful of those two places in the graph. Okay, so we can make the graph, well, actually, we need to start out by finding these, and then we can make the graph, just like we did in the previous video. Okay, the x-intercepts are going to come from setting the numerator equal to 0. Let me write this as a function. So to find the x-intercepts, we're going to set the numerator, or the top, equal to 0. So the x-intercept here is going to be the point -1, 0. And then we need to find the vertical asymptote. The vertical asymptote is going to come from setting the denominator equal to 0. Notice we cannot factor or reduce here, so that's not really an issue. So the vertical asymptote would be at x equals 1. All right, if you wanted to go ahead and do the whole graph here, we'll just add in all those other pieces that we have looked at in the previous video. It's probably good practice for us. The horizontal asymptote, remember we have that 3-part rule. Notice the degree in the top in the numerator is a 1. That's x to the first, and the degree in the denominator is a 1. So we're going to do leading coefficient over leading coefficient. There's a 1 in the top over a 1 in the bottom. So 1 over 1 would just be 1. All right, so let's put that into our graph, and then we'll add some extra points where we need to. So I have a vertical asymptote at 1. I have a horizontal asymptote at 1. And my x-intercept is at -1, 0. So I know part of the graph is going to be in this region. I need to pick a few points so that I can decide, is the right-hand side going to be above or below this asymptote. All right, so off to the side, plug in a couple points. Our vertical asymptote is 1. So just like before, I'm going to put that in the middle. That's where the graph is undefined right here. It breaks it into 2 parts. So I'm going to pick a couple of numbers on either side. All right, this is kind of crowded. I'm going to plug them into my function. And so if I plug in 0, I'm going to have -1. If I plug in -1, I'm going to have 0 over -2, which is just 0. That's my x-intercept. Okay. If I plug in 2, I'm going to have 3 over 1, so 3. And if I plug in 3, I'm going to have 4 over 2. Okay, so I already have this point, actually. So then I have 0, -1. And that's the left-hand side. Now I could pick a few more points if I want. Notice it's going to approach the horizontal asymptote at the end of the graph. And it's going to approach the vertical asymptote in the middle. So it looks sort of like that. On the right-hand side, I have the point 2, 3. And I have the point 3, 2. Same thing, I could plot more points if I want, but that's what these dotted lines are for. So I'm going to approach the vertical asymptote in the middle and the horizontal asymptote at the end. Okay, so that was a lot of work gone into making the graph. Are we looking for above, parts that are above the x-axis or below? I'm greater than 0, so I'm above. Okay. I've run out of colors here. I need to go buy some new pens, so I'll pull out I think I have some colored pencils right here. Alright, so here's my x-axis. Parts of the graph that are above, I have this little sliver here that's above once to the left of -1. So this would be part of my solution, all the points from here on. I don't know if you can even see that, but all right. And then this whole curve right here is above. Notice the vertical asymptote is a dividing line between parts that are below and parts that are above. So everything over here, okay, now we are never going to include the vertical asymptote in our answer. So this is definitely a round parentheses right here. And for this problem, we don't have the equals bar again. All right, if we did, we'd use the bracket. I guess I didn't pick very many problems with the bracket this time. But so this point is also not included because we're not equal to. So our final answer is going to go from -infinity up to -1, round parentheses because we're just greater, not equal to. And then we're not including 1 because 1 is where the graph is undefined, right here on the vertical asymptote, up to +infinity. Okay. Now, we've drawn this graph by hand. Wanted to give you some more practice because this is what we're learning in this chapter, right? You could definitely use your calculator. When you use your calculator, you do have to make sure that you identify where are the x-intercepts, where are the vertical asymptotes. Sometimes that's easy to identify, sometimes it's not. If you use the graphing calculator, I would definitely recommend using the table feature to try and identify these two things. That might help you out a bunch. Okay. We have one more here, I guess we'll do. For this one, I'm going to use it to show you the number line method. Okay, so for all of these, to set them up, we really need to have 0 on one side. We haven't really come across any that didn't have that. So I guess we'll do this one because it doesn't have that. All right, so if we don't have 0 on one side, we need to move everything over to one side before we start doing any of the other procedures we've talked about in this video. For a rational fraction inequality, we want to move this over, and we would really like to combine everything into one single fraction on one side and 0 on the other side. After we do that, we're going to identify both the x-intercepts by setting the numerator to 0 and the vertical asymptotes by setting the denominator equal to 0. And we're going to put these on the number line. Okay, so just like we did this with the graph, we're going to do the same thing, but now we're just using the number line, and we're marking those called critical values, right? Important spots where we're changing from values that are positive for the whole expression to values that are negative. Then, just like before, we're going to test the value in each interval, and I didn't put it on here, but we're going to write our answer with interval notation. Okay, so the first step would be to subtract this 3 over to the other side. And then I would really like to combine this into one single fraction. So to do that, I do have to do a little bit of fraction work. Groan, groan, groan. Okay. All right, if you want, you can think of this right now as 3 over 1. So to make it into a fraction that I can combine with this one, I need to have the same denominator. So I'm going to multiply the top and the bottom by x plus 1. And 1 times x plus 1 is just x plus 1. Okay, so now I can make it into one fraction because they have the same denominator. So I'll have x minus 3 minus 3 times x plus 1 all over x plus 1. Now I can do some simplifying in the numerator. So this is x minus 3 minus 3x minus 3 okay, so I have positive x and negative 3x, so that's negative 2x. Negative 3 and negative 3 together would be negative 6. Okay, phew, that's a lot of work. All right, so now we have done the first step, right? We have it all in one fraction. Okay, so now we want to find those critical values. So to do that, we're going to set the numerator equal to 0, and we're going to set the denominator equal to 0. Let me do that over here. So if we set the numerator equal to 0, and we solve, we'll add our 6 over and divide both sides by negative 2. Okay, this is going to be the x-intercept. I'm just going to label that. I know we're not making the graph, but it is kind of helpful maybe to think about what that is. Okay, and then the denominator down here was x plus 1. So if we set x plus 1 equal to 0, we get x equals negative 1. And as far as the graph goes, this was the vertical asymptote. Okay, notice on this one we're greater than or equal to 0. So we do have the equals bar. Finally, I got one of those in here. Okay, because we have the equals bar, we want to include the x-intercepts. The negative 3, that's what's going to make this whole fraction down here equal to 0. And I want to include that because I have greater than or equal to. However, the negative 1 is going to be the vertical asymptote. This is where this fraction is undefined. So this is never included. The vertical asymptote is never included in general, and it's not included in this problem. Okay, we're using the number line method. So we're going to plot these 2 points. All right, this is a good example because -3, remember, is smaller than -1. So -3 goes on the left. If you need to put a 0 reference point in here to help you remember that, that is kind of an important, if you put them in the wrong order, you are not going to get the right answer. Okay, I'm going to go ahead and pencil this in. We said -3 is included. -1, never going to be included because it's an asymptote. Then we're going to test a value in each region. So pick a number smaller than -3, -4. Pick a number between -3 and -1, -2. And pick a number bigger than -1, like 0. And we're going to plug these 3 numbers into our fraction right here. Okay, so if I plug in -4, I'm going to have 8 minus 6, so that's 2, over -3. So it's negative. If I plug in -2, I'm going to have 4 minus 6, so that's -2. Divided by -1. A negative divided by a negative is a positive. Okay, last one, if I plug in 0, I'm going to have -6 over 1. So negative. All right, I'm sort of referencing this quite a bit. So I'm looking for values that are greater than or equal to 0. That means the plus, right? Bigger than 0 would be positive, so that's plus. So I want the middle this time. So my final answer is going to go from -3. I'm going to use the square bracket because it's included, because I'm greater than or equal to, up to -1, round parentheses. All right, I hope this gave you a really thorough look at these 2 methods, the graphing method and the number line method. It is going to be very important when you take your test to show some supporting work. So I'm going to ask in part of the directions that you show a graph or that you show a number line. Even if you use your calculator to help you, you're still going to have to draw one of those 2 things to get full credit. So keep in mind, that's kind of important. All right, good luck with these. I hope you find lots of practice problems in the book and give these a try. Thanks for watching.